Hey everyone, and welcome back for another deep dive. You know how this works. We take some really complex research, the kind that makes your head spin, and we break it down into something, well, understandable and, dare I say, fun. Today, we're looking at something that's been causing a bit of a stir in the world of artificial intelligence, specifically with deep neural networks, or DNNs for short.
Yeah, DNNs.
DNNs, right? These are the, brains behind a lot of the really cool AI stuff we see. Like, imagine you have a system trained to recognize different fruits, apples, bananas, no problem. But then you throw a mango into the mix, same basic category, fruit, but totally different looks.
Right.
That change, that's what we call concept drift.
Hmm.
And it turns out it can really throw even the smartest AI for a loop.
That's a great way to put it. And the research we're diving into today really grapples with this concept drift challenge. They've developed this new system called, get ready for it, DeepStreamEnsemble. It's all about how to detect and, more importantly, how to adapt to this drift, especially when we're dealing with images, that messy high-dimensional data. Like, it's one thing if your spam filter has to learn a new type of marketing email, but it's a whole other beast when the very essence of what makes an image belong to a certain category starts to, well, drift.
Totally. So today we're going to try to untangle this concept drift thing, see how DeepStreamEnsemble tries to fix it, and figure out why everyone's making such a big deal about it. Oh, and here's a little spoiler alert. The secret sauce here is that DeepStreamEnsemble actually uses the DNN's own internal signals, kind of like its thought process, to figure out when things are changing and then adapt. No need to start from scratch.
Pretty cool, right? So first things first, why do these DNNs, as smart as they are, get tripped up when the data changes on them? It's like, imagine a student who's memorized a textbook, cover to cover. They can answer any question from that book perfectly. That's kind of how traditional DNNs work. They're trained on a fixed set of examples, a data set, and they assume that the data they'll see in the future will be pretty much the same.
So they become like specialists in what they've been trained on. If it's cats and dogs, specific breeds, they'll nail it. But throw in a new breed, one that looks different, and suddenly they might not know what to do.
Exactly. And even if the overall category is the same, like your fruit example, with the mango showing up, the GNN, if it can't adapt, might misclassify it. Or even worse, not even realize that something's changed.
Yeah.
And this is where it gets serious. The paper you sent actually points out some pretty scary real-world examples of this. They talk about, self-driving cars, those vision systems, trained on older car models. What happens when they encounter a new, sleek, aerodynamic design? Could be a recipe for disaster. They even mention a case, a collision with a bus, to really drive home the point.
Yeah, that's a bit unnerving. Now, this research we're talking about, it really focuses on concept drift in this high-dimensional data, like images. What makes images so much harder to deal with when the data starts to change?
Well, a few things. First off, just detecting the drift in images,
Yeah.
it's way more complex than in simpler data sets. Think about the amount of information in a single image.
Huh.
Every pixel, its color, its intensity. It's a lot compared to, say, a few data points in a customer profile. There's so much more that can change. Then, even once you've detected the drift, adapting the DNN, it takes a lot of time, a lot of computing power. And get this, sometimes this adaptation can lead to something called catastrophic forgetting.
Catastrophic forgetting. Now that sounds ominous.
It is. It basically means that as the DNN learns to recognize the new data, like our mango friend, it might start forgetting how to classify the things it learned before, the apples and bananas, like learning a new language so well that you start forgetting your native tongue. On top of all that, DNNs really shine when they're trained on massive balanced data sets. But in the real world, the data is always flowing, always changing. It's hard to keep things balanced and ideal like that.
So just to be clear, the paper makes this distinction between concept drift and concept evolution. Can you unpack that a bit for us?
Sure. So concept drift, as we've been talking about, it's changes within existing categories. The label's the same, like fruit,
Yeah.
but the examples within that category change. The mango, that's a new subclass. Concept evolution, on the other hand, that's like adding a whole new category. It'd be like our fruit classifier suddenly having to deal with pictures of vegetables, a whole new ballgame.
Yeah.
And the paper points out that detecting concept drifts can be trickier. The changes are subtler. Figure 1 actually illustrates this nicely. A mango still looks like a fruit, right? So the difference is less obvious than, say, a carrot appearing in a bowl of fruit.
Right, that makes sense. Okay, so with all this complexity, how are people currently trying to address this, and where do these methods tend to fall short, especially with these image data sets?
Well, the paper highlights a few limitations with existing approaches, especially when it comes to high-dimensional data. A lot of the traditional methods were designed for simpler data sets, fewer features. So when they're used for images, what they often do is they reduce the dimensionality of the image data, basically boiling it down to its key features, before they even try to detect the drift. But the problem is, you might lose some crucial information, something subtle that could signal a change. Then there's clustering. The idea there is that if the data is changing, the natural clusters, the groupings within the data, will change too. But clustering usually needs a bunch of new data points before it can spot a shift. So by the time it reacts, it's already behind.
So it's more like reacting than proactively spotting the change, huh?
Yeah, exactly. And when it comes to adapting DNNs to concept drift in this high-dimensional data, there hasn't been a ton of research, to be honest. A lot of the techniques we have actually come from this related field called online domain incremental learning, ODI. Now, ODI also deals with changing data, but its focus is more on accumulating knowledge, keeping everything it's learned, and it usually assumes you have all the correct labels for the new data. Concept drift methods, on the other hand, they're all about reacting to changes without needing tons of labels, and they prioritize the newest data. One more thing the paper points out is that a lot of studies that test these systems, they use synthetic data, like they'll add blur or noise to existing images to simulate drift. That's useful, but it doesn't really capture the real-world nuances of these subclass shifts.
Okay, so enter DeepStreamEnsemble, the hero of our story. It claims to be different, better. What's so special about its approach?
Well, the key is, DeepStreamEnsemble acts as a sort of intelligent wrapper around these pre-trained DNNs. It gives them the ability to detect and adapt to concept drift. Importantly, it does it fast. The idea isn't to retrain the whole DNN every time the data changes. That'd be a nightmare. The system's got two main parts, DSEDD, which does the drift detection, and DSE-Adapt, which handles the adaptation once a drift is detected.
Let's start with DSEDD, the detective. How does it actually figure out that the data is drifting?
The really clever part is it uses the DNN's own internal signals. It looks at the neuron activations in the hidden layers of the DNN. Think of these activations as the DNN's way of representing the image, how it encodes the features it's seeing at different stages of processing. The earlier layers, they might focus on basic stuff like edges and textures, while the deeper layers learn to recognize more complex stuff, shapes, whole objects.
So instead of just looking at the final answer, like, is it a mango or not? It's looking at how the DNN is seeing the image step by step.
Exactly. And then it processes these activations using this technique borrowed from content-based image retrieval, CBIR. The idea there is, find images that look similar based on their content. So here, they use a method to reduce the dimensionality of these activation patterns. They're basically picking out the most important features. The paper actually cites this work by Staszewski and others, 49 in the references. And they don't just do this for the whole hidden layer. They do it for multiple sections within those layers. They call them convolutional blocks. Then the output from each of these blocks, it's fed into this ensemble of super-fast learners. They're called Hufting trees, or HTBE. Each block gets its own Hufting tree.
Hufting trees, now there's a new one. Why are they so special for this task?
Oh, Hufting trees, they're awesome. They're these decision tree classifiers that are perfect for dealing with data streams. They learn super fast, make really solid decisions about how to categorize data, even with just a few new examples. And here's where it gets really interesting. The system then compares the predictions from the main DNN with the predictions from these Hufting trees. It uses this thing they call a novel accuracy volatility change detection method to do this comparison.
Accuracy, volatility. Okay, I'm going to need you to break that down for me. What's going on there?
Basically, the logic is if the data starts to drift, like those no mangoes start appearing, the Hufting trees, they're quick learners, they'll pick up on it fast, right? Their accuracy might start to change because they're learning from those internal DNN activations. The main DNN, though, it's slower to change because its knowledge is based on its initial training. So big difference in the accuracy between these two. That's a sign, a signal that concept drift might be happening.
Wow, so it's using the DNN's own inner workings to tell us when it's starting to get confused. So once DSED waves the red flag, what happens next?
DSE-Adapt steps in, right? Exactly. DSE-Adapt takes charge of the adaptation process. They call it a memory-based method. When a drift is detected, the system doesn't just focus on the very last data point. It looks at a whole window of recent data, maybe even a few windows before that, to figure out how to adapt.
So it doesn't just forget everything it just saw. It remembers a bit of the past.
Right. It also uses another set of Hufting trees. This time it's called the Adaptation Ensemble Buffer, or AEB. The AEB, it does get updated with the correct labels when drift is suspected. So it can adapt really quickly, like a temporary fix, while the main DNN adjusts itself more carefully. Then the main DNN gets partially updated using this new labeled data. But importantly, it can also hold on to some memory of the older data to avoid that catastrophic forgetting. And those neuron activations, they play a role in this adaptation too, guiding the system towards which parts of the DNN need updating.
And the amazing part is it does all this without having to retrain the entire DNN from scratch, right?
That's the key.
Yeah.
It's way more efficient, way more practical for real-world applications. And while the main DNN is updating, the paper mentions that the AEB can be used to classify new data coming in, so the system never stops working.
So they claim that DeepStreamEnsemble brings a bunch of new ideas to the table. What makes it stand out from what's already out there?
A few things. First, it's the first to really use this idea of accuracy volatility, comparing the main DNN with these fast-learning hosting trees as the main way to detect drift. Second, it's got this clever way of reducing the dimensionality of those complex activations, using ideas from CBIR, and it applies this to multiple parts of the hidden layers. The adaptation method itself is also new, combining those activations with the hosting trees to guide the DNN's updates. And they did a really thorough analysis of different drift patterns: abrupt, gradual, reoccurring, specifically in the context of those ODI methods we talked about. That's new insight for both fields. Importantly, they didn't just use synthetic data, they used real-world subclass images to test their system. That's a big deal. And finally, the fact that it can be used with pre-trained DNNs, no need to start from scratch, that's a huge plus for practicality.
It all sounds very promising, but theory's one thing, right? How did it actually perform in their experiments?
They really put it through its paces. They used several well-known image datasets: Fashion MIST, images of clothes, CFAR 10, and CFAR 100, which have a wider range of objects, different numbers of categories. They use a standard DNN architecture, VGG 16, pre-trained on ImageNet, a huge data set. So their setup is pretty typical of how things are done in the field.
And how did they simulate the concept drift in their experiments?
They did it by adding new subclasses to existing superclasses in the datasets. For example, in Fashion MIST, they might start with sandals and sneakers under the footwear category, and then they'd introduce ankle boots as a new subclass to simulate the drift. Table 2 in the paper actually lists all the superclasses and subclasses they used. They also tested different drift patterns: abrupt changes, gradual changes, reoccurring changes, even incremental changes where the existing subclasses slowly evolve. Figures 5 and 6 and Table 4, they show how these different scenarios played out.
Okay, so what were the main takeaways from the experiments? Did DeepStreamEnsemble live up to the hype?
It did, for the most part. In terms of drift detection, DSEDD, it generally beat other state-of-the-art methods like DDM, ADW, and others. They use the F1 score, a common metric for evaluating detection, and Table 6 shows that it consistently outperformed the competition across different data sets and drift patterns, especially in those tough, gradual, and reoccurring scenarios for Fashion MIST and CFAR 100. Now, they did mention that some novelty detection methods like MINUS and OCDD were good in specific cases for CFAR 10, but DSEDD was often faster, see Table 8. They also compared it to another new method, COD, and found that DSEDD was better on the more complex CFAR 100 data set and scaled better in terms of processing time.
So not just more accurate, but often faster, too.
Yeah, exactly.
Yeah.
Now, for the adaptation part, DSE Adapt, the results were also pretty good overall. For Fashion MNIST, it consistently beat other online learning methods, ER and MIR-RV, in terms of accuracy. And for CFAR 10, it also did well in certain drift scenarios. You can see the details in Table 7. What's important is that it was much faster at adapting the DNN compared to ER and MIR-RV. Check out Table 9. They did admit that it didn't perform as well on CFAR 100, which they think might be because there weren't as many training examples per class in that dataset.
Makes sense. More data for fine-tuning usually helps. So how did the whole system, DeepStreamEnsemble, perform when you put it all together?
When they compared it to other combined systems, like RSB, Tent CPE, Kata, DeepStreamEnsemble, generally had the highest overall accuracy across all drift scenarios and datasets. Table 7 and Figure 7 summarize that pretty well. And it did this with a processing time that was similar to the second-best method, RSB, see Table 10. They even did a statistical test, the Wilcoxon signed rank test, to confirm that the improvement over RSB was statistically significant. So yeah, the experiments pretty much back up their claim that DeepStreamEnsemble is a big step forward in dealing with concept drift in high-dimensional data.
That's impressive. So for our listeners out there, the big takeaway is this. DeepStreamEnsemble offers a way to make DNNs, those powerful AI systems, learn and adapt to changes in the data in real time without having to constantly retrain them from scratch. And it does this by cleverly using the DNN's own internal signals to know when things are changing.
Exactly. Think about the possibilities. Self-driving cars that are safer, more reliable in changing environments. Medical systems that can adapt to new disease variations or subtle changes in medical images. Fraud detection that can stay ahead of the curve. It's pretty exciting stuff.
And the paper even talks about what's next for this research, right? What are they looking at for the future?
Yeah, they mention a few interesting directions. One is testing DeepStreamEnsemble on even bigger, more complex, real-world data sets to see how it scales up. Another is seeing if the same principles could be applied to other DNN architectures. They focused on convolutional networks, but they think it might work for others too, some adjustments. That opens up a lot of possibilities.
It definitely does. So, as we wrap up this deep dive into Deep Stream Ensemble and the whole concept drift issue, here's something to ponder. With data changing faster than ever, how might these systems that can learn and adapt on their own change the technologies we use every day? Think about your own interests, your own field. Where could this kind of adaptable AI make a difference? If you're really intrigued, you can find the full paper in the International Journal of Machine Learning and Cybernetics. Until next time, keep those brains buzzing.